Hi everybody, welcome to your lecture on weathering. I'm going to do a little bit of a demo for you. You know, weathering is all about how to break down rocks, and one of the primary ways that we can break down rocks is with acid, and that's called chemical weathering, or it's a type of chemical weathering. So you might be wondering, where the heck do you get acid in the natural environment? You know, because usually acid, we think of chemicals and things like that. But of course, there are a lot of natural acids that just form. So I want to show you something. So this little guy right here, this is bromothymol blue. And what that is, you're probably, what the heck is that? Well, it's a pH indicator. It tells us whether something is acidic or basic. So I'm going to take a little bit of this, and I'm going to add it to pure water. So I just have some. Oh, this is a brand new bottle. So I have some pure water right here. Okay, so I'm just going to add a little bit. And I'm here at, working with dangerous chemicals at my desk, and that's okay. But just going to add a little bit there to my pure water, and you can see that my pure water turned blue, right? So I'm going to stir that up, and you can see that pure water it turns blue, right? Ooh, okay, that looks kind of cool. I could see my face through the. Wow, that's interesting. Okay, so anyway, that's pure water, right? Just normal water. It's blue. Blue means neutral. Okay. Now, on the other hand, I have this can of HEB seltzer water. It's absolutely pure seltzer water. It's not flavored. It's nothing but just carbonated water. Okay, so it's water with dissolved carbon in it, or I should really say dissolved carbonic acid in it. So dissolved CO2. So you can take CO2 gas and you can dissolve it into a liquid like water. You can dissolve it, by the way, into lava too. Lava absorbs a lot of CO2, but you can absorb it into water as well. And when it absorbs into water, it forms something called carbonic acid. It's actually a weak acid. So I'm going to show you this now. I'm going to pour some of this into my other one here. And I just kind of want you to see the difference. Okay, so there's my bubbly carbonated water, right? You all see that? Okay, bubbly carbonated water. Now I'm going to add some of the same pH indicator. We'll see. Do you think it's going to be blue? Okay, what's your prediction? You can see that rather it's turned kind of yellowish, right? So if I add more, you'll see that it's kind of a deeper yellow. Okay, so what does that mean? Pure water is blue with the pH indicator. The carbonated water is yellow. That indicates that it's acidic. Now, I can even do you one better. I can take this pure water, I'm going to put the acidic water, carbonated water over here, and I actually blow on this with a straw, and I can actually change its color. Okay, so if I start blowing on this, there's nothing really to it, you know. I should probably pour out a little bit because I'm going to get bubbles all over myself. Here we go. Okay, I'm going to start blowing. This might take a little time. Maybe I should pause this after blowing on it in a while and come back later. Pause. I'm still blowing on this. It's been a few minutes. No, it's not been a few minutes. It's been about 1 minute. Let's see if it's different now. Okay, I hope you can see that now it's not so blue. Remember how it was lovely blue? Now it is kind of a light green color. So it's kind of gone between, I haven't gotten it quite yellow like the carbonated water, right? That's really yellow. But I have gotten it greener just by blowing on it. And that's because the carbon dioxide from my breath is literally dissolving into this and changing the pH and making it more acidic, okay? So I just want to show you that we can actually change the pH of water by adding carbon dioxide to it, and plenty of carbon dioxide in the atmosphere, right? So it dissolves into the water, changes the pH of that water, and it can make it acidic. And you might remember there's a really important mineral that dissolves in acid. Y'all remember that from one of the other demonstrations? It's calcite. And you'll find that a lot of rocks on Earth are made of calcite, and that carbonic acid does a lot of work to dissolve the calcite away. So we'll see more about how this all plays out later in the lecture. Okay, so I'm going to switch you over to the lecture now. Welcome back, and now here's the lecture. So We're doing, like I said, lecture number 10 in weathering, and we're going to talk about our two main types of weathering. Let me get my pad, my pen pad. Whoops, there we go. And I also need my lecture assignment packet. And again, I keep reminding you, you know, if you need one of these things, they're here at my office. I have them for free. So I just know people have still been turning things in without, you know, doesn't matter. But just to let you know, they're here. So if you're printing them out like one by one at home, why not come by and pick one up for free? Okay. So anyway, lecture assignment number 10 is about weathering. So first thing you got to know is what the heck is weathering. So before I even show you that, I wanted to show you some kind of dramatic pictures of weathering. So this, maybe if you've ever gone out west, maybe to like Arizona, you might have seen stuff like this. This is called spheroidal weathering. You see all these things that look like round spheres, you know, and looks pretty cool. And a lot of people wonder, like, how did those spheres form? These like perfect like spherical boulders form. Well, they formed from weathering. Okay. This is Halong Bay in Vietnam. This is a type of weathering called karst. We'll talk about this later. But a very dramatic landscape, right, with these hills that are very steep-sided. And this actually comes from the collapse of caverns. So at one point, Halong Bay was just a place with a lot of caves. The caves eventually collapsed, and you're kind of like the roof of the caverns collapsed, basically. And now this is the topography that is formed. This is a really cool place. This is called the Stone Forest in Madagascar. There are lemurs there. So I can set you up to watch this. This is kind of cute. YouTube's going to scream at me about how I'm doing a copyright infringement, the BBC. But anyway, so this is the Stone Forest. And here are the lemurs that live there. They're pretty cute.
This most diverse group of primates has adapted to thrive all over the island, even here.
So anyway, I don't want to show too much of that because I don't want to use up too much time like that. But anyway, that is, whoops, here. That's where we are. Okay, that's the Stone Forest in Madagascar. It's another example of weathering. This is another example of a landscape formed by weathering. These are the Hoodoos in the Badlands National Park, South Dakota. Bryce Canyon in Utah, another very interesting landscape sculpted by weathering. Arches National Park in Utah, yet another really interesting landscape sculpted by weathering. And as long as Monument Valley National Park. So a lot of really interesting landscapes that are all formed through weathering. Okay, so anyway, I want to talk a little bit about it. It's kind of hopefully get you a little bit excited about weathering. You know, weathering, you might be like, oh man, that sounds really dull, but it is actually pretty cool. So what is weathering? Get ready for question number 1. What is weathering? Weathering is the breakdown of bedrock into smaller pieces. Okay, it's just the breakdown. I could even just say rock into smaller pieces. So, you know, the weather. What happens when you leave a car out in exposed to the weather, exposed to the elements, right? The weather weathers it away, it breaks it down, you know, and if you actually look at this car, it's actually a pretty good example of weathering. You know, there's all sorts of different ways this car is being broken apart, right? It's rusting, it's the tires and the rubber of the tires are decomposing, the metal is rusting and decomposing, the trees are, you know, with its roots tearing it apart and messing it up, right? So all these things happen not only to a car you leave out, a junker car you leave out in the forest, but also happen to rocks, okay? So weathering is the breakup, crumbling, destruction of solid rock, okay? So that's question number 1. So you can see that these rocks right here, this bedrock crust is being broken down, and there's these big piles of sediment that are left at the bottom, at the base, and those are called talus slopes. Okay, talus slopes. And what happens to all that weathered rock? Well, it gets carried away by the river here, right? So it's going to get carried away. We call that process, with a different name, we call that erosion. So I want to just make a distinction here. Let's see if I ask about this exactly. I don't think I have a real question about this, but it's a good thing to take notes on here. What's the difference between weathering and erosion? Because a lot of people just think they're the same, and they're not. Weathering is the process that breaks the rock into pieces. So this is weathering, right? The rock has been broken down into small pieces in the talus slope. Erosion is when that stuff gets carried away or transported away. Okay, so there's a big difference there. There are two types of weathering. Okay, so this is question number 2. There are two types of weathering. There's mechanical weathering and there is chemical weathering. Okay, what is the difference between mechanical weathering and chemical weathering? The difference is mechanical weathering breaks the rock without changing its composition. Chemical weathering breaks down the rock but changes its chemical composition. So here are two different examples. Here's a boulder that's been split, maybe by some kind of mechanical weathering process. I don't know which exactly. Here is some sandstone that has this really interesting kind of honeycomb texture pattern to it, and the way that you might, maybe even if you keep your eyes open, you might even see things like this. You can see this, especially rocks that are near the bay. You'll notice this sometimes. Like go to like a jetty. It's made of stone. You will notice this. I've seen this, for example, at Cole Park, at Indian Point. You can find this honeycomb weathering pattern. So that is a type of chemical weathering. Okay. So you got to know the difference between those, chemical weathering and mechanical weathering. The difference is one changes the chemical composition, the other does not. Okay. Now we're going to talk about 3 different kinds of chemical weathering now. 3 different types of chemical weathering, and one is going to be weathering of granite, carbonic acid called carbonation, and oxidation. Okay, it's not enough on your lecture guide to just write down those words. You have to describe each one of them. Okay, so just one sentence description of what it means. So how does granite break down? Well, it breaks down in a process called hydrolysis. So hydrolysis is when water reacts with the rock. And the very simplest kind of pseudo-chemical formula you could write for this is rock plus water gives you clay minerals. So actually, more specifically, what happens is it's water reacting with feldspars in the granite. You know that granite is composed mostly of feldspar. All right, here's another picture of beautiful spheroidal weathering in the granites. So this weathering and hydrolysis of granite often creates these rounded cobbles, rounded boulders that are almost perfect spheres. So hydrolysis, this is a very more accurate formula for hydrolysis and the weathering of granite. So feldspar in the granite, which is the most common mineral of the crust, plus water, which there's a lot of water in the crust, gives you kaolinite, which is a clay mineral. Kaolinite's a clay mineral. It's one of the clay minerals that we talked about in the minerals lecture. Plus aqueous silica, so that means SiO2 that's dissolved in the water, plus aqueous potassium bicarbonate, which is also dissolved in the water. Okay, so it's a very important thing here, and we'll get to this when we talk about streams and stream load. I want you to just kind of store this in your mind and remember that when the rocks are chemically broken down through hydrolysis, the water dissolves both silica and potassium bicarbonate. Okay, so that becomes important later when we talk about streams and stream load. So the stream water is often carrying a lot of dissolved minerals in it. Have you ever heard of like well water and it has dissolved minerals? Well, some of the dissolved minerals, for instance, come from weathering. Can carry silica, can carry potassium bicarbonate in this case. Okay, so there's even, if you want to get even nastier chemical formula, this is the same thing, all a balanced formula of exactly what the hydrolysis reaction is. You don't need to know that exactly for number 4. Like, you don't have to write out this exact chemical formula, but I do want you to put for number 4, what chemical weathering products are produced by the reaction of water with feldspar and granite? It's, first of all, kaolinite, clay mineral, and so this is kaolinite right here. This is the formula of kaolinite. It's a clay, and there's potassium bicarbonate and silica. Okay, those are the products. Okay, so that is hydrolysis. That occurs often, like I said, in granites, which are mostly composed of feldspars. Now, another Another kind of weathering that we have, chemical weathering, is oxidation. So you've probably heard of oxidation before. Um, Oxidation is basically rusting. It's kind of like rusting. Rusting is an example of oxidation. But it's just when iron in the rock and oxygen in the water react and form rust. Okay, so there's lots of iron in the rocks. You might remember there's a lot of iron-bearing minerals, and they can literally rust and create these very dramatic, sometimes red-colored rocks. You create the rust, right? Rust is red color. So I don't know if any of you have ever been to like Sedona, Arizona. You've probably seen like the really red rocks out there. If you ever get a chance to visit Sedona, Arizona, by the way, really a worthwhile place to visit. It's really, really cool. So here are some good examples of red bed sandstones. I don't know if these are from Sedona. I don't think they are, but they're the same kind of rocks that you would find in Sedona. So how do you get those red, very red rocks? You know, you might know here in Texas, maybe like in North Texas and Oklahoma, you get a lot of these like really red soils. So what happens is like the iron in the rock plus the oxygen in the water gives you rust, Fe2O3. Okay, so that is oxidation. Yet another type of chemical weathering is carbonation, carbonic acid. So I showed you right in the little demonstration how you can take the what do you call it? The carbonic water, carbonated water, and add some. It's actually has a acidic pH. Okay, so it has an acidic pH, and that acid is very good at breaking down certain kinds of rocks. One rock that it's very good at breaking down is, you might remember, calcite. You remember how in the minerals lecture we talked about how calcite breaks down with acid? So calcium carbonate, CaCO3 minerals like calcite are the main constituent of a rock called limestone. And whenever limestone comes into contact with carbonated water, and water just naturally picks up carbon from the atmosphere, right? Remember I showed you I blew into this water and turned it blue to greenish color, kind of bluish greenish color. But I made it more greenish just by blowing my own carbon dioxide into the water, right? So the same thing happens with water naturally. It becomes more acidic because it absorbs more carbon dioxide, okay? So name 3 ways. Okay, so number 6 is really, we'll get to that a little bit later, but number 7 says, what mineral is limestone mostly made of? Limestone is a very common rock. We're going to learn about it when we learn about sedimentary rocks next time. But limestone is made out of the mineral calcite, or a carbonate mineral, calcium carbonate, a calcium carbonate mineral. Okay, what kind of weathering is limestone very susceptible to? Carbonation. Okay, breaks down easily because it's made of that calcite. It breaks down easily with acid. So CO2, if I go looking at the next page here, it says, what reaction occurs between CO2 in the atmosphere and in the water? Well, it's right up there on your screen. So CO2 in the atmosphere reacts with water, and it makes this thing, which is carbonic acid. Okay, so it forms carbonic acid, and it changes the pH to the water, makes the pH lower, which means it's more acidic. Okay, so that kind of weathering by water, carbonated water, is very powerful against limestone. And so groundwater will pick up, some CO2 from the atmosphere. It will become acidic, and it will start to eat away at the limestone. So wherever you get limestone bedrock, you get like a lot of caverns and caves, and we call this kind of topography karst topography. Okay, karst is written up here. So over time, these caves will cave in. It'll make sinkholes, and then the last stage, you'll get that kind of Halong Bay, very dramatic landscape with these steep sides and maybe lots of sinkholes and things like that. And that's all from having limestone eaten away by carbonated water. Okay, so here's beautiful examples. There's all sorts of. This is Bull Shoals in Arkansas, but we have our share of really beautiful caves. If you ever get a chance to go to Natural Bridges, which is not too far away, you can see things even, I think, more spectacular than what you see up on the screen right now. So anyway, Very much worth a visit if you ever get the chance to go to Natural Bridges Cavern. Okay, so there's a little bit more about karst. I think I asked about karst. I guess I don't. Okay, that's all right. So, when you get all these caves forming, what happens sometimes is the caves collapse. So that's how you get sinkholes like this. So the ceilings of the caves collapse. And so, a lot of, like, especially in like Florida and Kentucky, Tennessee, you get things like this. So there's a real famous example of caves collapsing and forming sinkholes that actually struck the National Corvette Museum in Bowling Green, Kentucky, not too long ago. This was like a few years ago, or maybe I want to say like 2000 and maybe I want to say something like maybe like 2019 or something like that, 2018 maybe. So anyway, here's a sinkhole actually forming, caught right on camera in China. I thought this was crazy. Sinkhole forms, and then this dude just drives right into the sinkhole. I think he was okay, but it is funny. So physical weathering and landscape. So we talk about chemical weathering, but we also need to talk about mechanical weathering here. So mechanical weathering. So 5 things that we talk about. I give you 5 spaces there. Number 11 are jointing, frost wedging, root wedging, salt wedging, thermal expansion. Okay. So we'll talk about all these different things. So jointing. What the heck is jointing? Jointing is when, due to tectonic forces, like stress in the rocks, from the rocks moving with the tectonic plates, the rocks start to crack and crumble. Okay. And it will form sometimes very like nice, clean, what are called joints, which are like these nice, clean cracks in the rock. And sometimes the cracks are just like very straight. So these are vertical joints. This actually comes not from pressure or tectonic stresses, but this vertical jointing here, it's called columnar jointing, actually comes from the cooling of a magma body. So at one point, the Devil's Tower in Wyoming, or this example right here, columnar jointing, these used to be pools of basaltic magma, basaltic lava, and they cooled, and as they cooled and contracted, they formed cracks. So you might know that sometimes when things dry out or when things cool, they contract and they form cracks. Sometimes these cracks can be very like geometrical, polygonal. Another example of jointing comes from the reduction of pressure. So, when you have a magma body like this, the magma body is under extreme pressure under the ground, right? And when it comes to the surface, you release that pressure, it forms these pressure cracks. So can you all see these like pressure cracks that are forming here? You see how cracked this rock is? And it kind of is cracking. I hope you can see it's cracking into like sheets. That's very, very indicative of pressure reduction, jointing due to pressure reduction. So we actually call that exfoliation. This next picture I'm going to show you is so crazy. Take a look at this. So this is columnar jointing in a basalt. Okay, so nobody made this. I know it looks like man-made, right? But nobody made this. It forms this way naturally. And it's just from when the basalt cools, and as it cools, it cracks. And it cracks into this kind of polygonal pattern. So sheeting, so this is jointing that happens due to reduction in pressure from a magma chamber. So the magma chamber is very deep under the earth at one point, then it comes to the surface. When it comes to the surface, it reduces in pressure, and as it reduces in pressure, it expands, and as it expands, it kind of flakes off into sheets of rock. Okay, so that's called sheeting. Another term for this is exfoliation. So it creates exfoliation domes. So I want to show you these things. This is Yosemite National Park. There's an exfoliation dome. There's an exfoliation dome. Half Dome, which is a very famous rock formation, is an exfoliation dome. Okay, so these are all exfoliation domes. And it's what happens when a magma chamber rises to the surface. And it's obviously already cooled and solid, but it reduces its pressure and it cracks in these kind of flaking off these sheets, and we call that exfoliation. Okay, so exfoliation produced by sheeting. Okay. This is a really cool GIF, a really cool video that was caught of somebody literally witnessing exfoliation joints forming. You see that? And it almost looks like an explosion. So this person's on top of a granite outcrop, and they can kind of tell something's up. There's things cracking, and then all of a sudden, all the cracks form at one time. So they're literally watching mechanical weathering happen in real time. It's really cool. Very, very interesting. You know, people have all these cameras now, so they capture, on their phones, so they capture these things that are very, very rare occurrences to actually witness. So this is a really great video. So there you go, jointing. And what's cool about jointing is that jointing can often form these like really super geometrical kind of cuts to the rock. So like you can see, like this isn't just breaking like randomly, it's breaking almost like cleavage planes. It's breaking really precise geometric sort of pattern to the breakage. You get these blocks. Okay, so here you go, formation of joints. So another way that we get a mechanical weathering is from frost wedging. Frost wedging is when there is a crack in the rock, and the crack fills up with water, and then it freezes. And when it freezes, it becomes ice. And as you all know, ice expands, right? So you've probably done something like this in your life. Maybe you have, maybe you haven't, but maybe you try to put like maybe not a beer, but you try to put a Coca-Cola or something into the fridge or into the freezer, and it freezes, and what happens? It blows up. Or maybe you try to put some glass jars with soup or something, you want to save it, into the freezer. You fill it up and come back later, and the jars are cracked. What happened? Well, that's frost wedging. Basically the liquid froze, it expanded, and it cracks and destroys the glass. And it can do the same thing with rock, right? It expands and it breaks the rock apart. So it's called frost wedging. And that happens in places with a lot of freeze-thaw cycles. Do you think this happens a lot in Corpus Christi? No, not so much, right? Because we don't really get too many freeze-thaw cycles. But a place like Michigan or, Minnesota or Canada happens a lot. Okay. Here is something, though, that happens a lot in Corpus Christi, especially near the ocean. So remember I pointed out that honeycomb pattern of weathering to you? So you will find this sometimes. Gosh, that even looks like, is that like a tanker out there? This could even be Corpus Christi. But anyway, this is a type of weathering that forms with salt wedging. Salt wedging is similar to frost wedging. It's when salt crystals from the ocean start to grow in the cracks of rocks. And as they grow, they split apart the rock. Very effective in coastal environments and semi-arid, which we are sometimes semi-arid. Half the year we're semi-arid, if not arid, environments. So you will find this. And like I said, you can go to, this is in Sonoma, California, but you can go to Corpus Christi Bay, and you can find examples of this. Okay, so another type of physical weathering is something called thermal expansion. Thermal expansion, you might know if your windshield gets covered with frost. One of the rare times maybe we get frost in Corpus Christi. If your windshield gets covered with frost, you might know it's not a good idea to take boiling water and pour it on your windshield. Why is it not a good idea? It's because when you take glass and you put it, and remember that rocks are very similar to glass. They're silicate. Most of them are silicates, right? You take glass and you cool it or heat it up very quickly, it can lead to cracks. And the same thing can happen with rocks, right? If rocks are going through heating and cooling cycles day in and day out, it can lead to cracking in the rock, thermal expansions in the rock. Another thing is imagine if there's a forest fire, right? And then the rocks are heated up very quickly by the forest fire or by a brush fire, something like that. That can heat up the rocks very quickly and lead to thermal expansion cracks or thermal contraction cracks. Okay, same difference. So those are all the different types of mechanical weathering that we talk about. I just want to say a little bit of something on differential weathering. I don't think I ask any questions about this, but a lot of these really cool landscapes we see are from differential weathering. And differential weathering just happens when, certain rock layers erode more quickly than others, right? So you can see, like in this little GIF animation, the blue layer is more erodible than the orange layer. So you get these kind of interesting patterns that can form. Here's another example of that, where there were two dikes in a granite, and the black darker rock started to weather away, right? And you get this kind of interesting pattern. So it creates differential weathering creates a lot of interesting patterns in rocks. Places where, for example, there might be like a soft rock layer and a harder rock layer on top, you can get these pedestal rocks, where that softer rock layer is weathering more quickly than the harder one on top, and so it weathers that way. It's called differential weathering. So it's weathering at a different speed. Okay. That also happens because in deserts there's a lot of wind abrasion. That's actually another type of mechanical weathering, is abrasion. It's when sand is being blown, kind of like a sand blaster, and it erodes the rock away. Okay. Another thing I want to talk about, number 15, asks about biological activities. So biological organisms, basically, can also play an important role in weathering the rocks. So some examples of this are plant roots, right? Fungus, lichens, bacteria. A lot of these things, fungus, lichens, and bacteria, produce organic acids that attack the minerals. You might have looked around and seen rocks that seem almost like they're covered with a fungus. That fungus is actually not a fungus, it's a lichen. Lichens are they're so interesting. But I have to hold my tongue. I don't want to say too much about lichens. But lichens really are interesting because they're actually not a single organism. They're a symbiotic community of different fungus and bacteria that are living together symbiotically. And so they're kind of, give a little, get a little. And that's how they break down the rocks with organic acids. They extract some of the nutrients from them, and that's how they live. Okay. So the effects of climate on weathering. What kind of weathering mostly occurs in desert climates, do you think? So, a place like this, Corpus Christi, where we're not a desert, but we're kind of arid. We're close. Well, I shouldn't say we're close, but let me say this. We kind of have a little bit of a rainy season here in Corpus Christi, so during a large chunk of the year, we might not have any rain at all. So sometimes we're kind of almost like an arid climate, but we aren't arid because we get 33 inches of rain on average per year. 38 is average for the country. So you need 10 inches of rain to be a desert. We'll learn more about that when we talk about deserts. But anyway, so what kind of things do you think would happen in a desert? So you might be thinking maybe thermal expansion, thermal contraction, jointing, exfoliation domes, things like that. But there's not a lot of water. So remember, a lot of these things are associated with water. Think of all the weathering processes that we learned about that are associated with water. All the chemical weathering, carbonation, oxidation, hydrolysis, frost wedging, salt wedging, all those things are associated with water. What kind of weathering do you think you get in a tropical climate? A lot more, right? Because you get everything you get in a desert, plus you get all the biological weathering, and you get all the water. So you get all the maybe the only thing you don't get here is frost wedging, right? How about in a glacial environment? Frost wedging, right? And then you get things that maybe don't depend upon environment so much, such as jointing and exfoliation. Okay, so those are all I just kind of want you to be thinking. Number 16, a place like Corpus Christi. What would you guess? A hot coastal environment. What would you predict are some of the most important weathering agents here? One thing I realized that I don't address here is angle of repose, and it looks like I don't even have a slide on angle of repose. I talk a little bit about talus slopes. Let me pull up a slide. Didn't include this in the slides. I'm going to pause this for 1 second, and I'll pull up some slides about that. Okay, I found a slide here. So, uh, angle of repose. I just want to talk a little bit about this. So I mentioned talus slopes in the beginning. So when you have weathering of the bedrock at the base of the bedrock, it'll have a talus slope. That's all of the broken up weathered sediment material that forms at the base of a mountain or the base of the bedrock that's being actively weathered away. Okay, so those you can literally see this here. Notice how there is a certain angle. Whoops. There's a certain. Why isn't this drawing? I want it to draw. Whoa! Look at that. That's crazy. Boom. Such an interesting thing to be caught on camera. Okay, sorry. I'm actually just trying to teach you about. There we go. I got the pen now. But I want you to see how there is an angle here. Come on, pen. You are so frustrating. There we go. I hope you can all see that there is an angle here, right? So there's a certain angle there. I don't know what that angle is exactly. It's maybe, I don't know, 20 degrees or something. So there's a certain angle there that's called the angle of repose, okay? So there are different things that will make that angle of repose larger or greater. So you can maybe have a smaller angle of repose, like shown here with this fine sand, or you can have a larger angle of repose with this coarser sand, or an even larger one with this irregular. So you could have, usually talus slopes can even be up to 45-degree angles, okay? So that's a pretty steep angle. So anyway, what are some things that affect angle of repose? One of the things that I'm pointing out here is how large the particles are. So small particles will have a lower angle of repose. Small particles have a lower angle of repose. Larger particles like boulders and cobbles have a greater angle of repose. Another thing that can affect angle of repose is if the sediment is well-rounded versus if it's very irregular. So if the sediment is very circular and well tumbled and smooth, that's going to lead to a lower angle of repose. Whereas if it's very sharp and edgy and irregular, that's going to lead to a larger angle of repose. So, and also another thing that can make a difference here is the water content, So you know that you can build a sand castle, for example, with wet, damp, not wet sand, but damp sand, right? But if it dries out, what'll happen to your sand castle? It'll collapse. Same thing if the wet sand, if it gets too wet, it'll also collapse, right? So having the right amount of moisture can also affect angle of repose as well. So anyway, there's another video of a rock slide. That's kind of cool. We don't cover rock slides and things like that in this class. It's from earth science. But anyway, I covered everything that is in your lecture assignment, I think. Okay. So I'm going to leave it there. And I wish you a good week. Please let me know if you're having any problems with the class. And hope to see you next time. Bye-bye.